All right, we are recording really the first lesson of the year, 1.1 limits and continuity. Um, you have experience with limits, right? Yay, from your pre-cal. Um, limits, as we know them, are kind of everywhere, right? Like speed limits. What does that speed limit mean? Like if it's what, like back here on Ohio, right? Or actually on Kentucky, right? It's 20 miles per hour all the time, full time, 20 mph. So that's the speed limit. So what does that imply, or how does that relate to you driving? You go 27, you exceed the limit. That's interesting because most of the time, I mean, the word limit mathematically implies something that you cannot overtake or overcome. So I don't know what the rule is with the police officer. Like y'all think it's written down somewhere that as long as you're within 5 miles per hour, you can do that, and the cop won't pull you over. But it's not necessarily true. So uh, it's kind of a different meaning: speed limit versus calculus limit, because calculus limit is an idea of potential infinity, looking to see what it closes off at. But that's kind of a weird idea itself because infinity never ends. So if we were taking the mathematical definition of a speed limit, that means that on the back there, you could drive 19 miles per hour, you could drive 19.5 miles per hour, you could drive 19.7 miles per hour, 19.9 miles per hour, and you can get closer and closer and closer to driving 20 miles per hour, but you're never going to actually get there, okay? 19.99999 miles per hour. You approach the limit, you don't actually reach the limit or exceed the limit, right? Okay. So limits form the idea for the house of calculus. As we saw the other day, there's two parts. There's the derivative part, which is a division process, if you remember. Instead of delta y over delta x, which would be like a slope of a secant line, it's dy over dx, d meaning the differential of y and the differential of x. But notice it does look like your algebra 1 slope. D, remember, is not only differential, it means not measurable. So this would give you the slope of the tangent line. And then the other part is the integral. It's, I should probably put a y in here. It's going to be y, or f of x times dx. That's multiplication. And the s in this case means adding them all up. Those are areas, all right? But notice they're built on the foundation of the limit. Okay, now we're going to build the two halves separately, and notice there's lots of rooms in each of these halves because it does go back to infinity. New rooms are being discovered all the time. If you've ever read that great novel called House of Leaves, there's like a basement that has infinitely many rooms. It's kind of weird. Um, but we're going to eventually like quit building it, and then at the end of the year, towards the end, we're going to build a little garden shed in the back, which for y'all is going to be infinite series, and that's where you're going to put like your lawnmower and stuff. Okay, uh, because you do want to maintain your calculus house, right? You want to maintain those skills. AB does not build the little shed in the back. Okay. So to motivate the idea of the limit, I want you to think of the limit as a notion of motion. Okay, it rhymes, so it helps. A notion of motion. We're moving closer and closer and closer to something, and we're looking to see what it is we're approaching, if anything. Okay? In other words, what is the limit to our approach? What is going to stop us in preventing from going further? There's not always a limit. Okay? Now, for example, like on this one, if f of x equals x squared, we just want to fill in this number line chart, okay? So notice from the left-hand side, 2.999, 2.999, it looks like we're approaching the number 3. And then if we look at the numbers kind of coming back the other way, like this, 3.1, or I'm sorry, I didn't write that way. 3.1, 3.01, 3.001. So that appears to be approaching 3 from the right-hand side of 3. So let's go ahead and fill in this table. And this kind of goes back to our calculus etiquette, our calculus skills. The first thing you want to do is turn your calculator on. Yeah, there you go. My calculator doesn't work, sir. Did you turn it on? No. Okay, good, good. Now, because we're going to be evaluating a function repeatedly, it would be beneficial to put it in y1. So let's go to y1 and let's type in x squared. Now don't hit graph because we're not concerned with the graph right now. In order to fill this out, you don't want to go to the table because the table generates them for random values, although you could set it to input on independent variable. But I want you to get in the habit of doing it from the home screen because that's where we're going to be doing it. So alpha trace number 1, remember, I put it in y1, open parentheses, and let's type in 2.9, and we get 8.41. Okay, now that's an actual point on the graph, right? You can go stand at the point 2.9, 8.41. Let's go ahead and just inch a little bit closer to x equals 3. Bless you. You can either hit second enter, which is a nice way, bless you, to recall something. And then you can add another 9 and hit enter, or you can just type it in again. And we get 8.9401. So notice what happened to our y value. Did it increase or decrease? The y value increased from 8.4 to 8.9. So the y values are getting bigger. So x is also increasing. In fact, let's let it increase even more. Okay. Oops, I graphed it. I said I didn't want to graph it. Get out of there. Okay. So if I go back and add another 9, that's x increasing. What happens to my y value? It increases again, yes? Okay. But notice as it increases, it appears to be increasing by less and less and less, right? It went from 8.4 to 8.94, and then 8.94 to 8.99. So if we did that again, and I didn't write it in the chart, but if we did it again, right, put another 9 there, you're going to get 8.994. So it would increase again, yet again, right? And let's do it one more time. Just informally, I'll come back and I'll add another 9. And it increases yet again, okay? Now, as it increases from the left-hand side, does there appear to be a limit to its increasing? Or is it going to get infinitely large? Right. It is getting bigger every time. Forever and ever and ever, it's getting bigger and bigger and bigger. But it seems to be limited by the number 9. It appears to be getting closer to 9, okay? And if you do the same thing from the other side real quickly, we'll do 3.1. I just want you to get a feel here for the idea of motion, of notion. If I do 3.1, this is just on the other side of x equals 3, x being the independent variable, we get 9.61. And then to get closer here, we can't just add a 1 at the end, unfortunately. We got to go back and add a 0. So 0, 1. And we get 9.0601. So what happened to the y values there? They're decreasing, right? 9.6, 9.06. And if I do it one more time, just to fill out the chart, adding another 0, 9.006001. So it decreased again. Now, if you want to keep going, you're welcome to. The values from the right-hand side as we approach 3 also appear to be decreasing. But are they decreasing towards negative infinity? No, there appears to be another limit, right? They appear to be approaching 9. So we would say that 9 is the limit from both sides. So what do these values tell us about f in the neighborhood of 3? Yeah, we'll just say the y values in the neighborhood of 3. And neighborhood means on left and the right side. On the left and the right side. Immediately to the left and immediately to the right is probably a better thing to write, but immediately is a long word, okay? This lives on a through street, right? We have neighbors to the left and neighbors to the right, okay? So that's the neighborhood. Immediately to the left and right, as x gets closer to 3 from either side, the y values appear to be approaching, the y values approach y equals 9, okay? So 9 appears to be the limit from the left and the right. Now, based upon that, what do you think the value of f of 3 is? That is, if I went to the graph and actually stood at x equals 3, what do you expect to stand at? What y value? It would be very reasonable to think 9, right? If it's so close to 9 from the left, and so close to 9 on the other side from the right, then it would appear if you actually stood there, you'd be standing at 3, 9. Okay. Now, what is the value of f of 3? It is 9. How can we figure that out? Well, we could do it from the calculator, right? We could just come in here and we can actually type in a 3, right? And we get, oh, 9. F of 3 is 9. Or you can just plug it in by hand, right? F of 3, if you plug it in, is 3 squared. We could do that one. That's 9. Okay, cool. So what better way to figure out what's happening in the neighborhood of x equals 3 than to go stand at x equals 3 and say, hey, I'm standing at 9. But does that tell you about the neighborhood? If you're standing at your house and you're not looking left or right, you're just standing there, that doesn't tell you about the neighborhood at all. That just says, I'm at this house. To know what's going on in the neighborhood, you actually have to look left and you have to look right. You'd be like, those guys next doors, they party all night long. These people over here, they're deadbeats, right? I think they're drug dealers. That's a bad neighborhood. Okay? So, interestingly enough, that function we say, of course, we know what it looks like, right? It looks like this and it looks like that. So not only do we live on a through street, but there's no potholes in the street, right? As you're driving, you could drive straight through. Zoom, zoom, zoom. Okay? We say the function's continuous at 3. All right? So in that case, if you want to know what's happening in the neighborhood, you can actually go stand at that spot and say, oh, this is at 9, and then that can inform you because it's continuous that the values in the neighborhood are also approaching 9. By neighborhood, we mean a really small neighborhood on either side.